So let's begin the third part of this course, where we will start the mechanical interface in order to set up and solve our model we just created. We will start up mechanical, and then we'll briefly go over the interface, and then guide you through setting up the model, which includes assigning materials, creating connections, meshing, setting up the boundary conditions, and applying the loads, and then finally solving the model. By the end of this module, you will understand the process for setting up the analysis and will be able to use the same tools for any other model you may create on your own. So let's pick up from where we left off in the project schematic view. Now that we created our geometry, we can see that cell number 3 is up to date with the green check mark. This means we are now ready to launch mechanical. We can do this by either double-clicking on cell number 4 or right-clicking and then clicking on this edit button right here. So let's go ahead and click on this right now. So once inside the mechanical interface, at the top here we have the menus toolbar. So we have some basic menus such as the file menu, where you can save a project, export a project, the edit menu, the view menu where you can change different view parameters, the units menu where you can change your units, the tools menu where actually an important one here would be maybe the solve process settings, where if you click on this here you can click on advanced and change the number of utilized cores for your analysis. And after that here you have the help menu. Next to the main menus we have a few toolbars here at the top. The first one right here is called the standard toolbar, which contains commonly used application commands such as the solve button for solving an analysis or the section view button for creating sections. Below it is the graphics toolbar, which contains commands that control the pointer mode or cause an action in the graphics window. Some important ones are the select mode here, where you can change from a single select to a box select, the geometry filters where you can choose, let's say, a vertex or a body filter. So if we want to only choose a point on this geometry, we can click on this point and now we can select the points on the geometry. Or if we wanted to only filter faces, we can click on the face, and now we're clicking only on faces. Next are the basic rotate, pan, and zoom buttons. There is also a zoom to fit. If you're, let's say, too zoomed in, you can go and click on this and it will zoom to fit. We have the set ISO button. So let's go ahead and do this right now. This resets the isometric view. So as we can see here, the lifting lug is a bit towards the side, and we kind of want to maybe reset the isometric view to something more like this. So we can rotate this using the middle mouse button or the rotate view. And now once we have this view in place, we can click on the set ISO. And then now we reset our isometric view. So let's say if we rotate it around and we click on this button here to get back to the isometric view, we can see now that the lifting lug is facing upwards. So following the graphics toolbar is the graphics options toolbar, which provides quick access to features that are useful for controlling the graphical display of the models. So for example, the first button right here, which is Show Vertices, essentially toggles on and off the vertices of the model. Another button right here is the wireframe, which can toggle on or off wireframe mode. Another one here would be Show All Coordinate Systems. This one here would be to set random colors, but this is for loads and name selections, which we will get to maybe a bit later. And finally, some annotation preferences, where you can change a bunch of options here for your annotations. Next, we have the Explode View Options toolbar, where you can explode your model using this slider right here. And following that, we have the Edge Graphics toolbar, which provides access to graphic features pertaining to the edge display. However, we won't be covering these two toolbars in this tutorial, so let's go and remove them right now. We can click on the View tab right here, and click on Toolbars, and then click on Explode View Options to remove the exploded view options, and then once again to click on the Edge Graphic Options to remove that as well. So now we have slightly more space. Next we have the Context toolbar, which dynamically changes based on the type of object selected in the tree outline box here on the left. So because these options keep changing, I will cover them as we go along in the tutorial. Next we have the Tree Outline window, which provides a structured list of the objects included in a project, and it will be the primary interface element of the application. And right below it is the Details View window, which gives details about each object selected from the tree outline. So selecting, say, the geometry object from the tree outline, We can now see attributes and controls for this object, such as the total volume in this view. Next, in the center, we have the geometry window, which displays the model and where you can manipulate the visual representation of the model. Right below it, you can see three tabs, the first one being the geometry tab, which is the one that we're in right now, the second one being the print preview for printing, and the third one called report preview for generating reports, which we will go over later on in this course. Finally, we have the status bar at the bottom, which gives you some basic information such as the current units of the project. Now that we've covered the essentials of the mechanical interface, let's go ahead and start setting up our model. Expand this button by clicking on the plus sign right here. Now, as you can see, we have all our components under this tree window right here. So we have the base, we have the lifting lug, and we have our 4 bolts that we created in Geometry Modeler. Now, each one of these bolts can be further expanded, and now we can see the individual components of each one of these bolts. Now, in order to assign a material to it, as you can see here in the details view, it is yellow, which means a material input must be defined. So in order to do that, we can click on this arrow, and now you can see that we can either assign a new material, import a material, or we have a material right here called structural steel, which we already defined earlier in this tutorial. Now, instead of selecting it right here, I want to assign all of these bolts the same material. So what I can do is click on bolt 1 right here, which contains all these subcomponents of the bolt, and assign the material directly right here by clicking on the arrow again and clicking on structural steel. Now, this changes the little question mark on the left to a check mark, which means that this material is now up to date because it has now been assigned a material. We can now continue to do the same thing for the other bolts by selecting, let's say, bolt number 3 and clicking on structural steel, and we can even hold Control and select, let's say, bolt 2 and 4 and assign structural steel as well. Now, if I collapse these, we have the base and the lifting lug left. Now, we could go and create a different material and assign a different material for the base and the lifting lug, but to keep this tutorial simple, we're just going to use steel for all of the components. So once again, for the base, we're going to go into the material assignment and click on structural steel, and for the lifting lug, we will click on structural steel as well. Now our geometry has a green check mark and it is now complete. So now we can go ahead and collapse the geometry object. Now, next here in the tree outline is the coordinate systems, where if you expand this, you will see that you have a global coordinate system already set, and you can see that the origin is 0, 0, 0. Now, let's say if you wanted to create a new coordinate system, you can right-click on this object right here, click on Insert, and then click on Coordinate System. Now, with this, you can create a new coordinate system based on, let's say, a geometry selection, or you can even create it based on a named selection, or even offset it from the global coordinate systems by an amount that you desire. And this is very useful when defining loads and boundary conditions. However, we won't be really using it too much in this tutorial. So we can go ahead and right-click on this one and then click on Delete, and then we can click on Yes. Next up, we have the Connections object, which defines connections between 2 or more parts or bodies. So let's go and click on the Connections object right here, and now we can see something called Details of Connections. Now, the subcategory is called Auto Detection, so this means that Ansys will automatically detect connections by default. So if 2 objects are very close together, Ansys will go ahead and create a group here, which is called Contacts. And inside this group, you can see that it will create a bunch of contact regions. Now, if we select this first region, we can see the contact that Ansys created for us automatically. The contact is between the face of the base, and the target is the bottom face of the lifting lug. So you can see here that it brings up a body view, which on the right you have the contact body view, and at the bottom here we have the target body view. So in each one of these views, you can rotate to see exactly where it's highlighted. So in red is the base and blue is the lifting lug. So you can see here that this is the contact between the base and the base of the lifting lug. And the contact type here in the definition is bonded. Bonded means that Ansys will join the nodes together and will not allow any movement between them. Now, as you can see, we have other ones here which are called no separation, frictionless, rough, frictional, and forced frictional sliding. However, the important ones to note are bonded, frictionless, which means that there will be no friction between the surface, and frictional, where if you would select this, you can go ahead and apply a friction coefficient between the two. So let's go ahead and enter a friction coefficient of 0.2 for this example. Now once you change the definition of the contact, Ansys will automatically rename this to frictional, which is the type, and then base to lifting lug, which are the contact and target body surfaces. Now there are more contact settings, such as advanced and geometric modifications, however we will not cover them in this tutorial. Now let's say you want to change the default contact settings for Ansys, and let's say you didn't want Ansys to automatically import all these connections. You can go ahead into the Tools menu and then click on Options. And then under Mechanical, you can see a tab called Connections. And in Connections, we have different things such as, let's say, the tolerance slider for the tolerance detection between the two surfaces, and then whether or not, let's say, you were including face-to-face surfaces, face-to-edge surfaces, etc. And as you can see here, the default type now is bonded, so that's why all of these contact regions are bonded by default. So if you were to change this, this would change the settings in Mechanical, so all future connections will always be as you defined here. But now that we're in the project, and we let's say wanted to remove this default contact group, we can right-click on it and then click on Delete, and then click on Yes. So now as you can see, we have no more connections that are created. Now let's say we wanted to create our own manual contact region. We can right-click on Connections, click on Insert, and then click on Manual Contact Region. After clicking on this, we can see that the details require two options. We need the contact and the target surface. So let's click on the contact surface, and using the Face Filter button, we'll click on this surface right here. Next, we'll click on the Apply button here. So now that's selected the base as the contact surface. Now we want to select the base of the lifting lug as a target surface. But as you can see here, we can't really see it right now. So what we're going to do is, using the body select filter, we can click on the base, right-click, and then click on Hide Body. Now you can see we have access to clicking on this bottom face. So using the face filter, we'll click on this face, and then click on the target, and then click on Apply. Next we can right-click in the window and click on Show All Bodies. So now we have both bodies here selected, and we can see we now manually created a contact region. Now in the definition type, as again you can see that the default is bonded. Now this would be a long process to do for each one, so in our case, the automatic connections that Ansys created for us are actually very useful. So what we're going to do is we're going to delete this contact group by right-clicking and clicking on the Delete button, clicking on Yes. We're going to right-click on Connections, insert a connection group, and inside the connection group we can right-click on it and then click on Create Automatic Connections. So this will recreate all the connections that we just deleted previously. So now let's actually define each one of these connections correctly. Let's click on the first one again. We know that this is from the base to the bottom of the lifting lug, and we want it to be frictional with a friction coefficient of 0.2. Next we'll click on contact region number 2. We can see that this contact is between the face of the bolt and the inner face of the base. Now for this tutorial, we're going to leave this as the default type, which is bonded. We want to actually have this bonded to the base. Next we're going to click on contact region number 3, and we can see that this is the same thing as contact number 2. We would like to keep this bonded. Number 4 is as well, it's the bolt to the base, and number 5 is the same thing. Now what we can do to better organize this is actually hold the Control key, and selecting contact regions number 2, 3, 4, and 5, we can right-click and click on this group here, which will create a new contact group for us. And we can call this Bolts to Base. Next we can go ahead and click on contact region number 6. We can see that this is the surface between the bolt and the lifting lug's base plate. In this region we're going to go and change the type of this definition from bonded to frictionless, because we want to allow sliding in this region. Now in contact region number 7, we can see that this is the bottom part of the bolt head touching the top surface of the lifting lug. We're going to want to keep this the default bonded value. Next, let's move on to contact region number 8. We can see that this is the same thing as the contact region number 6 that we changed. We want to change this again to frictionless. Contact region number 9, once again, the bolt head to the lifting lug, bonded. Number 10, we're going to change this to frictionless. Number 11, we're going to keep it bonded. And number 12, frictionless. And finally, contact number 13, we're going to keep that bonded as well. Next, we can group these up again. We can click on these frictionless contacts here, holding the Control key, right-clicking, and creating a new group. Now we'll call this group frictionless. Next, we can click on these four holding the Control key, right-clicking, creating a new group, and call this bolt to lifting lug. Now we've organized all our connection groups. So let's go through them once more just to make sure. The first one is the base to the lifting lug. The next are all the bolts to the base. Next are the lifting lugs to the bolts, which are the frictionless connections. And the last one is the bolts to the lifting lugs, which are the bonded connections. Now that our connections are done, we can go ahead and minimize this object and proceed on with the mesh. So by clicking on Mesh in the object tree, we can see in the Details view different types of defaults that will be applied. So we can see that the physics preference for the mesh is mechanical. If you're doing something like a CFD analysis or a nonlinear mechanical analysis, you could go ahead and change the type of physics preference as required. But we're going to just leave this as mechanical for right now. Now you also have some options for the default sizing of the mesh. So expanding this function right here, you can see that you can choose different types of sizing options. And one of the most important ones here is the element size, which if you click on here is default, but you can change this to any value you want. And then finally you have down here the statistics tabs, which tells you the amount of nodes and the number of elements that the mesh has created. So as you can see here, we have a lightning bolt, which means that it's ready to be generated. So let's go ahead and just see what the standard mesh will give us. Now to do that, you can either click on the mesh and click on this update button right here, or you can right click on the mesh and click on generate mesh. Now let's say your model was a bit too big, you can go and just click on preview surface mesh, which will generate a very quick mesh on the surface and won't model the 3D elements on the inside. So let's go ahead and click on the preview and surface mesh and see what that gives us. So there you have it. There's the default mesh given by Ansys. Now if you want to do a full mesh, we can right click on this and then click on generate mesh. Now as you can see, this mesh is somewhat coarse, and the elements here are a little bit too big for this analysis. Now the reason I say this is because if you look at the lifting lug, you will see that there is only one element across the thickness of the lug. And as a general rule in finite element analyses, you typically require mesh with multiple elements through the section in order to capture the stress and deformation gradients more accurately. So before refining the mesh in this area, let's go ahead and see the statistics on this mesh that was generated. We can see that we have about 4,000 elements and 15,000 nodes. So to refine the lifting lug model, let's go ahead and right-click on the mesh, and what we're going to do here is click on the Insert tab. Now here you have a few options. The first one is called the method, which will determine the type of meshing algorithm used. To name a few would be the tetrahedron or hex dominant methods. The next one is called sizing, where you can change the size of the elements. After that we have contact sizing, which creates elements of the same size near the contact area. And then we have refinement, where you can select specific areas to refine in the mesh. And finally, we have a few other options which I won't get into for this lesson. So let's go ahead and choose the first one, which is the mesh method. So after clicking on mesh method, we can see now that we have something called the automatic method, which has been selected by default. And to the left, we have a question mark, again indicating that some parameters are missing in the details window. So the first thing it asks us is to select the geometry for the method that we're choosing. So in this case, we're going to select the whole model. In order to do that, let's switch from the single select mode to the box select mode right here. Now with that selected, let's drag over the whole model and select all the objects in our model. Now once that's done, click on the No Selection here in the geometry and click on Apply. Now we see we have 14 bodies selected. Now under the method here, under Definition, we can change this from the automatic method to a few other options. Some of the other options are tetrahedral elements, hex dominant elements, sweep method, and a multi-zone method. Now tetrahedral will only allow tetrahedral elements to be created in the mesh. Hex dominant method will try to convert as many tetrahedral elements as possible to hexahedral. The sweep method tries to create a mesh with wedge elements that are suitable for rounder or curved based objects. And finally, the multi-zone mesh method, which is a patch-independent meshing technique, which can decompose the geometry into mapped regions and free regions, so therefore you can have a combination of hexahedral and tetrahedral elements at the same time. So in our case, we're going to choose the multi-zone option since we have both rectangular-shaped objects and sweepable objects. Now after clicking on multi-zone, we can see that the mapped mesh type is hexa, which is what we would like in our case. And for the other controls, we're going to leave them as default for now. Once that's done, let's go ahead and right-click on the mesh and click on Generate to see a preview of what we have so far. After applying the multi-zone method, we can now see that the lifting lug's elements have been somewhat converted from tetrahedrals to hexahedral elements. This is better because if we look at the mesh count, we can see now that we've reduced our number of elements from about 4,000 to 2,500 elements. However, we can see that these elements are still slightly too coarse for this analysis. So I'm going to go in and right-click on Mesh, Insert, and now we're going to use the option called Sizing. So let's click on that right now. Now once sizing is selected, it'll ask you again to select the geometry that you would want to apply a sizing to. So in this case, we're going to go to the body filter, change our select mode to single select, and we're going to select the lifting lug. And then we're going to click on Apply. Now in the definition here, we can change the element size. So instead of having default, we're going to change this element size to 5 millimeters. Now once that's done, let's go ahead, right-click on Mesh and click on Generate Mesh again. Now we have a much more refined mesh for lifting lug. Now I can't really see the mesh of the bolts clearly, so let's go and hide the base by right-clicking on the base and clicking on Hide Body. And let's also hide the lifting lug by clicking on the lifting lug, right-clicking, and then clicking on Hide Body once again. Now if I zoom in, we can see that we have the mesh of the bolts, which are not too bad. However, in this region, we're going to apply a preload, so we want to have the mesh slightly finer than what it is right now. So in order to refine the mesh in these regions here, we're going to right-click again on Mesh, and we're going to insert another sizing. Now, instead of using the body filter, we're going to click on the face filter. And we're going to select each one of these faces using the Control key. Now, once all 4 faces are selected, click on the Apply under the geometry. Next, under the element size, we're going to change it from the default to 2 millimeters and hit Enter. Now let's go ahead and update, and this time using this button right here. Now in order to see the mesh, let's click on the mesh object here in the outline window. Now you can see it divided the mesh here with 2 millimeter spacings instead of the default value. Now that the mesh of the bolts are good, we can right-click in the graphics window and click on Show All Bodies to show all the bodies again. Now as you can see, after applying the face sizing, we get some error messages that says the selective body meshing is not being recorded, so the meshing may be not persistent on an update. This is just telling us to double check our meshing every time we update our geometry. So we can go ahead and ignore this message for now, and we can close out the messages. Now that our mesh is complete, let's go ahead into the Static Structural Object in the Outline menu. After clicking on Static Structural, we can see that we have the option to change the environment temperature from 22 degrees to any value that we want. However, we're going to leave this at 22 for now. If we click on Analysis Settings, we can see that we have a few options here. The first one being Step Controls. Step Controls is where you can define the number of steps of your analysis. So in our case, we're going to use 2 steps for our analysis. The reason for this is that we're going to apply a first step or a first loading case, which will be the preloading of these 4 bolts. Once these 4 bolts are preloaded and secure the lifting lug to the base, we will then apply a second step, which will be the force or the bearing load that will be applied to the lifting lug ring. So let's go and set this number of steps to 2. Now the current step number and the step end time we could leave as default, which is 1 and 1 second. Now under solver controls, we will leave it as the default parameters. But let's say you were doing a nonlinear analysis, you could go and change the large deflection setting to on, which will allow for large deflections. That completes the setup for the analysis settings. Next, we're going to apply our boundary conditions. So in order to do that, we can click on Static Structural, and we have two options. We can either click on the toolbar here to add a support, or we can right-click on it here, Insert, and add a fixed support. Now a third option is actually going into the graphics window and using the face selector, selecting this base, right-clicking, insert, and inserting a fixed support. So as you can see, there are many ways of adding boundary conditions to your model. So let's go ahead and use this method by right-clicking on Static Structural, Insert, and clicking on Fixed Support. Now because I had this face already selected, the geometry has already been selected as this face. So we can click on Apply. So this fixed support will fix the base in the X, Y, and Z directions, as well as the rotation in the X, Y, and Z directions. Hence, this support will be completely fixed. The next boundary condition that we need to add is the load. So what we're going to do is we're going to right-click on Static Structural, we're going to Insert, and we're going to insert a bearing load. Now the bearing load is used for cylindrical surfaces only, where the radial component will be distributed on the compressive side using the projected area only. So because this is only for cylindrical surfaces, let's go and click on this surface right here and click on Apply. Next, instead of defining the load with a vector, we can click on this Define By and change the vector to Components. Now here we can enter the components X, Y, and Z in newtons, or we can also enter it here in the tabular data window on the right. Now as you can see, because we have two steps, we have the time 0 to 1 and then 1 to 2. 0 to 1 will be our preload step, so we're not going to want to add any forces in these two steps. So we'll add our loads in step 2, and we will put 1000 for Y, and we will put 7000 for Z. Now if we click on step 2, we can see that we have a little arrow which shows us the direction vector of the force. Now the final step is to add the bolt pretensions. So in order to do that, let's hide the lifting lug and the base. So let's click on the lifting lug and holding Control, select the base, and right-click and click on Hide Body. Now let's just zoom in a little bit. And here what we're going to do is, using the Faces filter, we will select each one of these faces. Right-click, Insert, and we're going to insert the tool called Bolt Pretension. Now with the bolt pretension selected, let's move this table data over a little bit to have some more room. And we can see again it's divided into two steps. So the first step, we're going to add a load, and the bolt pretension load will be 2000 newtons. Now in the second step, we're going to lock this pretension value, so we're going to change the load and double click in this area here, and we're going to change it to lock. So essentially this will lock the 2000 Newton preload in the second step where we apply our bearing load. Now we want to do this for the other three bolts, so let's right-click on Bolt Pretension and click on Duplicate. Now click on the face selector, and we're going to change this face to this one over here and click Apply. And then right-click again on Bolt Pretension 2, click on Duplicate, click on the face, click on this one, and then click on Apply. And then we will proceed for the fourth one, Duplicate, click on the face, click here, and then click on Apply. Now if we select all of these, we can see that we have 4 bolt pretensions. So now that the 4 bolt pretensions are set, we can right-click in the graphics window, show all bodies, and then click on Zoom to Fit in order to get an outside view again. And now we're ready to solve our model. So let's go into the tree outline again and click on Solution. And now to solve the analysis, we can either right-click on Solution and click on Solve, or in the toolbar here we can click on Solve. So let's go ahead and click on this button right now. Now as you can see, Ansys will open up a window here, which is the status window of the overall progress for the solution. Now at the same time, if you click on Solution Information, you can change the solver output to Force Convergence, and you can see the Force Convergence graph window. Now the Force Convergence graph window shows you the calculated force and the force criterion needed in order to solve the problem. So in order to solve each step, the force convergence must be below the force criterion. So you can see that it took about 4 iterations before it solved the first load step, and then up until 11 iterations before it converged the second step. Now that we have our solution, you're ready to move on to the next module where we'll be going over the results.